On a rectangular piece of cardboard with a perimeter of 17 inches, 3 parallel and equally spaced creases are made. The cardboard is then folded along the creases to make a rectangular box with open ends. Letting x represent the distance between the creases, find the value of x that will maximize the volume enclosed by this box. Alright, so always starting with the diagram, it says we have this rectangular piece of cardboard, and we don't know the dimensions of the cardboard, we just know that the outside perimeter is 17 inches, and there's 3 parallel, equally spaced creases made. So, something like this. These are my creases. I'm folding this piece of cardboard. And it says, let's let x represent the distance in inches between the creases. So it looks like x is going to be this horizontal distance here. I'll mark all of them as x. And our goal is to eventually maximize volume. So I always like to begin with the goal as well. So the goal is to maximize volume. So if we want to maximize volume, then we want to write an equation for the volume of this box. So it might help us to actually write, or draw, excuse me, a three-dimensional picture rather than a flat two-dimensional picture of what the box looks like. So if I fold along those creases, I'm creating kind of like this long rectangular box. Something like this. And then x would be the dimensions of the base here. So when we go to do volume, we know volume is length times width times height. But we're missing a piece of information here. So going back to my original diagram, let's look at my original rectangle. I have all these little labels of x. I could go ahead and put them on the opposite side of the rectangle because they would be equivalent. Opposite sides are going to be congruent. And you'll notice then what I'm missing here, I don't know the height of this rectangle. So you could call this h if you wanted to. You could call it y. It doesn't make a bit of difference. I'll go ahead and call it y. And so both opposite sides then would have a length of y. So that length of y on my three-dimensional box picture would correspond here to that length of y. So now when I create my volume equation, length times width times height, I'm going to have x times x, those are the dimensions of the base, times y, which represents the height of the box. In other words, my volume equation would be x squared times y. Now, what's wrong with this equation? You'll notice we have two inputs. We're inputting the variable x and the variable y, and then we're outputting the variable v, which is no good. We don't want two inputs. We want just one input and one output. So we need to eliminate one of these variables. So hopefully there's some sort of information in the problem that is a constraint that's going to allow us to write what I call the constraint equation. So our constraint equation. So if you read through the problem again, you'll notice that it did give us that the perimeter here, the perimeter of the original rectangular piece of cardboard was 17 inches. So 17 is a constraint. So now we're looking at the original diagram, the original rectangle. The distance around the rectangle is 17. So if we're adding up then, this side here, we have x plus x plus x plus x. In other words, that would be 4x's, 4x. Same with the opposite side. That's also going to have a length of 4x. So we're going to end up with 4x plus y plus y. If you look at the four sides of my rectangle, we'd have 4x plus y plus y. In other words, we have 17 is equal to 8x plus 2y. As your constraint equation. And the purpose of this equation is we want to solve for a variable and then substitute so we can eliminate one of the variables in my volume equation. So it doesn't matter which variable you solve for, choose whatever is easiest. I'll go ahead and solve for y. So I'm going to subtract the 8x and then we'll divide by 2. So when I divide by 2, you have two options. You can just divide the entire left side by 2 like this, which would be fine. Or you can think of it more as term by term division, which is actually my preference. So I'm going to divide each term by 2. So 17 divided by 2 let's see, we're going to have what, 8.5? 8.5, since it's an exact decimal, I'll put it in decimal form. 8.5 minus 8x divided by 2 then would just be 4x. So this is my constraint equation that relates x and y. And now I'm going to substitute that into my volume equation, so that I now have a volume function in one variable. So I'll come down here for that. So volume is equal to x squared times y, but now I have this new equation for y, 8.5 minus 4x, which you could leave as is. I'll go ahead and distribute since it's a fast one. 8.5 x squared minus 4x cubed, and this is going to be my volume model. It's my function that relates x, which is the distance in between the creases, and the volume. So now you can go to your graphing calculator to graph this function, and we want to find the maximum. And as you're graphing it on your graphing calculator, it's good to have an idea of what we expect the graph to look like. So remember, because it's degree 3, we know the ends will point in opposite directions. We expect it to be an S-shaped curve. But because of this coefficient, the leading coefficient is -4, we're expecting our S-shaped curve to eventually point down. It will fall eventually. So if you need to pause the video to go ahead and take a second and graph it, then please do so. I've gone ahead and graphed it, and we kind of luck out on this one. We don't even have to adjust our window. We get an S-shaped curve that looks something like that when you plot it on your graphing calculator. Going back to our goal, the goal was to find the maximum volume. We wanted to maximize volume, so you'll see we have a maximum, and that maximum occurs right there. So go ahead and use your calculator to calculate the maximum, and let's write down the coordinate, and then we can decide what the coordinate actually means. So in doing so, I'm getting a maximum of approximately 1.4166, 5.6863. There's more decimals than that on my calculator, but I'll just copy down the first few. Now remember, the calculator is stuck with x and y. But that's not really what this coordinate represents for us. You have to take a look at the function that we actually put into our calculator. The function here, there it is in our calculator, was inputting an x and getting out a v. So this is actually better labeled x, v. So x was the distance in between the creases. If we round to 2 decimals, that would be 1.42. Going back to my original problem, let's see, what were we measuring in? The perimeter up here at the top, it says the perimeter was 17 inches. So x was going to be measured in inches, so that would be 1.42 inches. Let's try that again. 1.42 inches is the distance in between the creases on the original piece of cardboard. And then the maximum volume obtained in this scenario, the maximum volume, rounded to 2 decimals, would be 5.69. And since it's a volume, then the measurement would be cubic inches for the units. 5.69 cubic inches will be the maximum volume you can get in this scenario.